Merhaba. Hahn lemmayı ve Hahn teoremini ispatlamıştık. Şimdi bir iki tane kısa uygulamasından bahsetmek istiyorum. Öncelikle Hahn teoreminin ne söylediğini hatırlayalım. X gibi bir vektör uzayım vardı. Bunun bir alt uzayı y vardı. P gibi bir tane fonksiyonelim var. P fonksiyonelim pozitifli homojen ve subjektif functional olarak geçiyordu X üzerinde. Okey, diyelim ki y üzerinde psi her zaman p'den küçük veyahut da eşit olsun. Hahn teoreminin söylediği şey bu durumda bu psi'yi y'den x'e öyle extend edebilirim ki hala p tarafından domine edilir. Hahn teoreminin söylediği şey buydu. Bir tane uygulamasını göstermek istiyorum. İlk kısmına bakalım. X bir normal vektör uzayı olsun. Y de bir vektör alt uzayı olsun. If psi is a bounded linear function along the subspace y, then psi has an extension psi star to all of x with the norms coinciding. The norm of psi star is the same as the norm of psi. Okay. Söylediği şey bu. Şimdi bakalım. So let's pick some psi in bounded linear functions on y, and let's define m to be the norm of psi, which is given by this expression. And let's define a positively homogeneous subadditive linear functional p by p of x equals m times norm of x. This is defined on x. Birazcık küçültebilirim belki. Okay. Now by definition of m, I know that psi is bounded by p on the space y, and Hahn theorem then says that I may find some extension of psi, which is denoted by psi star, whose restriction to y is psi, and at the same time it's still dominated by p, which is given by this, on the extended space x. So I have found some psi star for which this is satisfied. Now if you replace x by minus x here, then this time you obtain if first you may have a look at here, then this will be bounded by p of minus x, which is the same as this part, and by linearity this guy is equal to minus psi star of x. So I can conclude that the absolute value of psi star of x is bounded by p of x, which is given by this expression or this expression. Okay, so basically I combine this and this inequality to conclude that psi star of x has length less or equal to this quantity over here. And from here, if you take the sup over all vectors with norm 1, then you obtain the norm of psi star is less or equal to the norm of psi. So this proves the first inequality, and next I claim that psi star has norm greater or equal to the norm of psi. Okay, in order to show this, let's pick some epsilon positive, and let's choose some x in y in the subspace such that its length is 1. And if you look at the value of our function at that point, then it's bigger than the norm of psi minus epsilon. How can I do this? By just using the definition of the norm. It was a sup, so I may choose an element as close as I want. Then if you look at the length of psi star of x, this is the same as psi of x, the length of psi of x, and psi of x is bigger than the norm of psi minus epsilon. But this is true for any epsilon positive, so we get the norm of psi star is greater or equal to the norm of psi, and from these two observations it follows that the norm of psi star is the same as the norm of psi. Okay, this is the first part. So we have found an extension psi star to all of x with the norm of psi star are the same as the norm of psi. This is quite a useful result. Let me tell you a few other corollaries. I won't detail these. Take it as a reading exercise. So this part is saying the following. If you choose some non-zero vector x in X, then this is saying that you may find some bounded linear functional for which psi star of x is the same as the norm of x, and the norm of psi star is equal to 1. It's pretty straightforward in this case. Basically, you take the subspace as the span of x, define the linear functional by this, and it satisfies. And the result will follow. Okay, another one. For every x in a normative vector space X, we have the norm of x is the same as a supremum over all non-zero bounded linear functionals, absolute value of psi of x divided by the norm of psi. Okay. Now, do we need to look at this? Let's go over it. It seems quite easy. Let's see. Now, if you take any psi in the dual, then by definition of this norm, I know that psi of x will length less or equal to psi, length of psi times the norm of x. Okay, so if you take the supremum, if you divide both sides by the norm of psi, non-zero guys, then you obtain this inequality. And if you take the sup over all bounded linear functions, then you obtain inequality for one part of this. And for the second part, we will choose a specific psi star, which was the content of part 2 of our previous theorem. So if you look at the right hand side, this supremum, this will be greater or equal to the length of psi star at x divided by the norm of psi star. This is just a specific guy, and in that construction this had length norm of x, and so this turns out to be equal to norm of x. So result follows from the result follows for the first claim. So if you combine these two, then it's okay. Hence, if x0 is such that psi of x0 is equal to 0 for all psi in x star, then x0 is equal to 0. You always obtain 0 here, so x0 needs to be 0. This is what it's saying. Okay, let me lastly state this corollary in this video. Let x be a normed vector space, then bounded linear functionals on x separate points, which means the following. If you have two distinct points, x and y, then you may find some linear functional f in the dual such that f of x is not the same as f of y. Again, this follows from the second part of the previous theorem. I will stop this video here. Bu videoyu burada nokta koyacağım. Bundan sonra second dual ile ilgili bazı tartışmalar var. Bunu sanırım Hilbert uzaylarını tartışırken yapacağız. Ama dileyenler şimdiden bir okuma yapsın burayı. Burada birkaç tane typo var ama size yolladığım notlarda düzeltilmişti diye hatırlıyorum. Görüşmek üzere.